Right. Okay. So welcome again. Thank you very much. So as I mentioned, we'll go through all the use cases. So in C-Scale, the project started with 6 use cases from the proposal stage. So that's what we call the native use cases. And they'll go first presenting. Then we have the open call use cases. So for open call use cases, we have many. Maybe not everybody is here, but I see the majority of them are present, so that's very good. And again, I'll go through the submission, the date of the application, more or less, approximately to go through them. So I think without further ado, first use case presenting will be Aqua Monitor from Deltares. I don't know if Bjorn or Jab, are you guys going to dive in?
Hey, Sebastian.
I have a question, Sebastian. Can you?
Yes, Anne, please. Yeah.
Can you give a rough timeline between the the different use cases? Just because we may not be able to attend everything.
Yeah. The thing is that's a bit tricky to give an estimation. Hopefully, everybody needs to stick to the assigned time slot. But
we have an assigned time slot. Sorry, I didn't see that. Where is it?
No. It's not. Okay. Because basically, not everybody confirmed, and then for the presentation, we said more or less about 8 minutes maximum, if possible.
Yeah, but we don't know how many use cases, and we don't know when we go and when we don't go.
Yeah. Okay. So I can give you an estimation.
Sorry.
Sebastian,
yeah.
Maybe you can ask who can attend until a specific time. They go earlier.
Yeah,
we didn't know who's going to participate, basically.
Yeah. Anytime restrictions?
Yes,
yeah, anytime restrictions. And do you prefer to go earlier or later, or?
So I'm away between 10:30 and 11:30 CET.
Okay. That should be fine because actually Pangeo was one of the latest.
Then it's perfect.
Yeah. Great. Yeah, you should be fine. Don't worry.
Okay, I am already breaking the rules because I do 2 use cases, so I just have one presentation for both. So
not a problem.
Yeah,
That's
yes.
Perfectly fine because those use cases are related. Fine.
Yes, they are for sure related. So
exactly.
So for everyone who does not know, I am going to cover Aqua Monitor and also global Waterwatch projects in C-Scale. So I'm starting up a presentation and now fighting with second screen, but after that we will all be happy. Yes. Let me share screen now. Screen 2. Okay. Is my second screen visible or first screen? So with the presentation full screen visible for you?
Yes,
you confirm?
Mm-hmm.
Okay, thanks. So yeah, I would like to introduce the work that we have done so far and a bit of the opportunities on C-Scale for Aqua Monitor and Global Waterwatch. So I'm Jaap Langemeyer from Deltares, and these are I will first start with Aqua Monitor and then cover Global Waterwatch at the end of the presentation. So first, of course, we have to start with what is it? So I think Aqua Monitor is an algorithm using optical satellite data, so passive satellites, and it looks at the last 30 years at changes from land to water and vice versa, and it uses these optical imagery to over the whole world, so it has a global scope to get a view on where the changes are in water. So I think what is important to realize is that we look at long-term changes at multiple missions. So it goes from Landsat 4 until 8, and also uses Sentinel-2. And we can use, I would say, it uses composite images over time. So we create yearly images from all the available satellite imagery from all these missions, and we try to harmonize it and create one, let's say, image per year. And based on that, we calculate, let's say, quite a simple regression to see over the water indices to see whether we see some changes. And currently, the prototype, or let's say the online version, if you go to the link or search for Aqua Monitor, is in Earth Engine, which is Google's, let's say, black box. Well, it's not totally fair, but it's their proprietary server system. And of course, this is needed because we cannot host this multi-petabyte sized image collection of all this satellite imagery, because we have a global focus, right? So it needs to work anywhere on Earth, and it also needs to work fast. Of course, we saw that OpenEO, which is also funded by this Horizon program, was a great opportunity for this, because there's been developments in the OpenEO platform, which offers big geodata processing software. It offers, let's say, data and compute, and it's just one language for operating on spatial data. So if I just create, let's say, my code in the Python interface, then I can talk to any of the C-skill providers. And this is, of course, also great, let's say, combination with C-skill, because I can write code in one language, just one version, and I just have to switch providers and it should always work. That's the idea behind it. And that's, of course, a good proposition for us, because then, yeah, we can also leverage not only just this Google system, but we can also try to see if we can run this on, let's say, C-skill infrastructure. So for us, this was a logical, let's say, technology choice. And for the infrastructure providers, they deploy OpenEO as a service for us, so we can just log in and start developing and running our algorithms. And they also host the data for us. Currently, we have an interactive notebook that implements the algorithm for any area of interest. The data is currently limited by the backend provider. So currently we're working with INCD for data in Spain, and hopefully with INFN for Italy data as well. And of course, we had big help from Vito, because they have a lot of maintainers from the OpenEO platform and a lot of data, so that I could get started early. And now the INCD has installed and tested the deployment and the data. So I'm looking to scale up the data and the algorithm, and to check the performance to see if it's this would really, let's say, be a candidate for future algorithms and for future work for us. So it's already great, because let's say it looks feature complete at this moment for us, because, well, we can just fully replicate the algorithm. And this is, I think, already a great success. And let's see about the performance later. And for Global Waterwatch, this is also a satellite, optical satellite product. We are currently developing this ourselves, also on Earth Engine, and it's a website currently, but of course behind it is still, let's say, some data product where we calculate for a database of a certain number of reservoirs from every image. So this one uses not a composite product, but it uses singular images, and there we check out what the water area is, and we hope to also move to water volumes in the near future. And then we can sort of give a good estimate of water availability, and we can also see, like, for example, I took a reservoir in Spain. I just wanted to show here like all the reservoirs that we have in our database, but then I clicked on a single one. I don't want to show interactive demo here, but then you can see, for example, for a large reservoir in Spain, that you can really see the trend over the last few years where, of course, it's becoming quite a lot drier. So here it looks a bit the same. So that's why I'm doing two use cases, let's say one presentation, but the aim is slightly different. So we keep track of surface water availability, and we change track changes per image. So it's I think even computationally more expensive than the previous algorithm, which just takes averages over a year and then does a lot of calculations on it. But it also uses like data from 1985, so also quite a long history, and also the same number of missions with the same multi-petabyte dataset challenges. And of course, these 72K reservoirs that we are tracking can be anywhere on the planet. So yeah, this is also a global product. And currently we have implemented it. So still really happy with the let's say custom or user-defined functions that you can create using just Python code, so that we could indeed test the OpenEO functionality and see that we can implement the algorithm. But at this moment, we're still waiting for the results from the previous project for Aqua Monitor to see how well it scales up. And we are also looking for to see how fast we can get the data in, because of course, with the C-Skill, we may be able to get the data directly from the providers instead of going via Earth Engine. So it's like we skip the middleman, let's say. So this is the aim for the next few months. So this is just a razor quick overview of the two projects. So if you have any questions, then please do share.
Thank you very much. Yeah, there was a question about having the repo open and public, and it is. I shared the link in the chat. Also, it's been recently tested with the EEI binder service. So basically, you could directly run it there as well. The goal is for all use cases, we start with a private repo if that is more comfortable, but then the end goal would be, it would be nice, not mandatory, but nice to have the repo public, so we can share the results with everybody. And that's the case for Aqua Monitor, which is the link in the chat. Hara?
Did I manage to raise my hand?
Yes, you did.
I did. Okay. Yeah, I was wondering, because Aqua Monitor is one of the use cases that have been running the longest since the start of C-Scale. What was the most successful aspect and the most troubled aspect for you? Let's put it this way.
I think for us, the most successful aspect was for sure the fact that that we got a lot of support from, let's say, the OpenEO community, so that it was not, of course, without struggles, but quite smooth to implement the algorithm. And I think it's both a bit success and difficult, is that we had quite some difficulties with getting this OpenEO backend installed at the different providers. So this month we got the good news that the test succeeded and that we can start testing on not just Vito, who are like I'm not sure if I'm bypassing people now, but it looks like they did a lot of effort for this OpenEO platform and the backend and all the infrastructure, and now they had to replicate it somewhere else, and this was quite challenging. But well, eventually, of course, now it looks like it succeeded, and we have to start testing and scaling. But I think this took quite a long time. So that was a big challenge for, let's say, the community as a whole to get this complicated system ported somewhere else. Yeah.
Thank you very much.
Andres?
Yeah, just to educate myself, have you considered using radar satellites for water body monitoring, or
Yeah. Oh, sorry. Can you repeat the question?
Have you considered using radar satellites,
Okay.
similar
Yeah.
technologies?
Yes, I know that this is for sure possible and already being done. So I think for me, for this global Waterwatch, we are still actively developing, so enough to do at this moment. But I think for me personally, I would love to investigate also different types of products from satellites to see if it can enhance, let's say, the view, because I saw some great successes also in I forgot right now, but there's many like let's say flood monitoring tools, or at least these kind of software that really effectively can use let's say Sentinel-1 to get the water extents, and it looks quite promising. So it would be a shame to not invest in it, let's say. Yeah, but thanks for the
Thank
tip.
Okay, thank you. Any other question? Okay, so then I think I propose we move to high C now. High C is another native use case from C-Scale, and Loritz, I see you are basically going to present, right?
Yes, that's correct.
Okay, good.
So let
Thank you.
me do that. Which one? Can you see the screen?
Yes, we can.
Okay, perfect. So thank you for giving us the opportunity to present these use cases. And we are continuing with another Deltares use case. So it involves water for sure, that I can guarantee. And in this case, it's deploying a workflow that supports coastal modeling practically. And because our models can do hydrodynamics and water quality, that helps us to support both type of modeling. And we are going to showcase how that is being done and how that is being distributed over different providers. And the team is Björn, well-known colleague, and myself. And of course, a lot of support from other colleagues. So in terms of the challenges or the main scope of the use case, well, as I mentioned, it is about coastal modeling. We are using our software, which is Delph3D Flexible Mesh, that also creates specific requirements. And the scope for C-Scale was also to test interoperability between different infrastructures, the scalability of computations, and the performance of combining different type of infrastructures. In this case, we are experimenting pre and processing cloud and more of the heavy computation on HPC. And we work together with actually 3 different providers, GRNet, Cloudflare, and well, we used Chestnut resources for a while. So just a bit elaborating on the name, it's called HiC because that was a previous Horizon project, and the solution was developed there. That is important to state, and we are porting that. And that solution was basically to serve different industries in the coastal domain, namely aquaculture and port authorities. And that means that we are calculating basic hydrodynamic variables like water levels or currents, but also we are using it for water quality applications related to, for example, oxygen and temperature. That's quite important for the cages, fish cages. And ultimately, this can become an early warning system for oil spills, contamination like harmful algae bloom. So it has a wide range of application, but we are focusing here on the portability. So when we consider this use case, we had the main challenge that modeling workflows are rather complicated, starting from these model schematization, which is an art in itself. So that we skipped, but all the rest we have covered in a automatized workflow. So we are able to get input data, pre-process it for our own software. We are able to deploy and run the simulation in different infrastructure. and we can post-process it to visualize it. And in terms of if some of you are more visual, this is how it looks like on a more visual workflow. So basically, we worked with the Greek domain in the agency. That's where the aquaculture in our use case was located. And then, of course, we have to download a range of input data. Here, we just highlighted the open boundaries from Copernicus Marine Service and some meteorological forcing from ECMWF. But then everything needs to be pre-processed. We are working here with different Python scripts, but are ultimately packaged. But I will show the workflow more from the technical side. And then once it's pre-processed, we run our model, and we wanted to help users to directly access it. That means we are offering post-processing that converts the unstructured grid to a more structured and easily with 1 or 2 lines of X-ray code, you can directly visualize it. And we have set up a Jupyter hub for that, Jupyter notebook. So in terms of technical solution, how it looks now, the workflow, we have different scripts to retrieve ERA5 from ECMWF through their API. We also have, we are connecting to Motu API to download the biogeochemical and physical boundaries. And then we have, and that is now in one container, the download container. We also have different containers for generating the boundaries. That is tidal boundaries, physical and biogeochemical, and the meteorological ones. And then we have our software, the L3D Flexible Mesh, available. Of course, it can be natively installed, but it's not as always as easy. So we also have it available on Docker Hub and in Singularity. We can execute that and then post-process it with yet another Docker component, and we have some visualization in, as I mentioned, in Jupyter Hub. So what's being done also is to have an automatic workflow. In its most basic version, you just use some simple solutions like cron tab or batch files. But what we are working on now is to have it more automatic with the help of Sebastian, and Bjorn is working to use snake make steps to have an automatic workflow, and in that sense, automatic or scheduled forecasts. And the other element is to make use of the HPC for computation. And Nikos from GRNet is helping us to provide a solution for that. So that is about the workflow. In terms of successes, before you ask for it, I think we are quite proud that we could finalize and standardize the workflow components, because they were written in various different scripts, ranging from MATLAB through Python 2, 3, and not really nicely. There were no arguments. It was not that logical. So that was a major work to standardize things and Dockerize them. We were able to open and deploy virtual machines in GRNet, CreoDS, and Chestnut. We had a successful training internally at Deltares, but also then in Prague in the EGI conference. We also deployed the L3D at the HPC of GRNet. So I think based on the scope that I presented at the beginning, we demonstrated interoperability, and I will show you that we also tested scalability. The performance of combining different resources, it's still pending. So that's our focus, and of course the snake make workflow. And just to show the scalability, we have tested our own resources. So we have a cluster at Deltares, which has virtual nodes and then bare metal. But then we also benchmark against the virtual machine and HPC. What you see here is that our software is partitioned on the left side. You see the CPU cores. So we partition our simulation, and it's really memory intensive. So it's not that you have to increase the partition until infinity and you will get better performance. It has some kind of optimal curve. This was just a test where we had 2 or 15 days forecasts. And you see that in this case, I'm covering myself, but yeah, it's eight partitions were best. So there is always room to work with the providers. They help to find these optimal curves and compare bare and virtual and HPC with MPI installed natively or from the Singularity. So we had quite some experiments here. And what's pending, as I mentioned, well, we work with a quite nice GitHub page that is managed by Björn. And as I mentioned, he's working on the SnakeMake, and we are working with Nikos on the HPC hybrid workflow. And we are hoping to use more and more resources, which we have the potential to do it because we are able to deploy yearly or multi-year simulations and operational forecasts. But this is something that comes after we have the automatic workflow set. Just if you would like to have more information, we have a quite well managed Confluence page, an active GitHub page, and we even have a news item that was posted on the C-Scale website. So I hope that I did not run too much over time. But thank you for your attention. And Björn is here, I hope, because he's also happy to contribute or answer any questions.
Thank you, Lorit. Yeah, it was spot on. 10 minutes. Brilliant.
Okay.
Thank you very much. Yeah, good. Any questions from the audience? Okay. Yes, Tina, please. I think we have a problem with your audio. Is it only me? I see your mic open, but I don't hear you.
Do you hear me?
Yes, now yes.
Okay.
Now we can hear you.
Sorry, my mic was not working well. So my question is, like, I heard that you use also MPI on Singularity on HPC cluster. My question is that, do you plan to test that on the OpenStack cluster as well?
Well, I think there is quite some backlog on what we can do. Right now, what we said that first priority is the SnakeMake, and then deploying on GRNet's infrastructure, so they help us. I don't know what are the implications to perform other tests, but I don't know if Björn, you want to add to that, but what we have experienced that the MPI in Singularity performed basically equally as the native or the MPI installed on the infrastructure. So I don't know if we need further tests because we had previous projects doing such tests. So if it's not really mandatory, I don't think we will focus on this.
Yeah. Okay. Now I was just wondering that maybe as the network connection in the OpenStack cluster might, affect.
Yeah.
Might not work very well for the MPI. So I was wondering about that. And what's the size of MPI job that you run normally?
That really depends on the size of the model, Tina.
Yeah.
So in this case, we're running a relatively small model, which is not partitioned over too many cores. But I think on the example that we have is we were partitioning it over 8 nodes on the HPC, or cores. I can't remember exactly. But yeah. It really depends on the size of the model. And this particular example is relatively small, so it can run on a single VM in the cloud.
But I have colleagues who work with climate simulations now with the same software, and that application has 200 cores. And yeah, so it can be scaled up, of course.
Okay, thank you.
Okay, thank you. There is another question from John in the chat about is this a single node or multiple? I think there are multiple nodes involved in the execution, right?
Yes.
Okay. Okay, good. Right. Thank you very much. Don't forget to send me your slides after the presentation, after the meeting today, so I can share them with everybody as well after the meeting. Good. So now I think, thank you, Lorenz. I think we can then move on to the next use case, On my list, I have a possible candidate. It's LSDA, for example, from Deltares.
Yep.
Okay, just hello.
Let's see. You should see my screen, right?
Yes, perfect.
Yes, perfect. All right, so I will be presenting a little bit about the LSDA use case, where we changed the name slightly to remove the emphasis a little bit away from droughts, but more on the discharge forecast, so also including high flows. We don't have a very nice abbreviation as the other ones, so sorry for that. Yeah. All right, so I decided first to start off, why do we need this workflow, and why is this workflow interesting for other use as well? I think a main issue where we're all familiar with is water safety and security. We have many regions in the world who depend on water, both on high water or low water, so floods and droughts, for example. But at the same time, there's also many regions across the globe where we have limited data or limited models available, where we would still need this information to get a bit more detail on how much water is available and if there's too much or too little water forecasted in the coming period. And then as thirdly, to remove the hassle of manually triggering a workflow once there are forecasts available. So this workflow trying to solve these three issues by providing hydrological simulations that use forecast data to provide sort of an outlook into the potential future for the coming months that can in practice be used to issue flood forecasts, for example, or drought warnings or any of those. We use globally available data, so the workflow can be deployed anywhere on the globe to provide these simulations, and the forecasts are run automatically, or the hydrological simulations are run automatically when the new forecast data is available. So just a visual overview of how our workflow looks like. I will not go into all the details, but so you have a bit of an idea of what we're doing. And our workflow essentially exists of three steps. So we have a pre-processing step, we have a run model step, and we have a post-processing step. Where the pre-processing step take care of downloading the data that we need and converting them into the input that the hydrological model need. And the data that we're downloading is ERA5 and CS5. Now we'll come back to that later as well. And we're downloading that from the Copernicus data storage. Now we're running the model. We need to run a catch-up and a forecasting mode. I will get back to those as well. And we're running the WFlow hydrological model, which is the model we developed at Deltares, which is written in Julia. And then finally, once the model has been done running, including the forecasting, we can do some post-processing to plot the results of the model run. We currently have this workflow running at the Surf infrastructure on Surf Spider, where the workflow is triggered automatically once every month when there's a new forecast available, which is done with a cron trap, and then the workflow is triggered once the data is there. So these are the three steps. So first is the pre-processing step, where we download the last month of ERA5 data to make sure that the hydrological model is up to date with the most recent states, let's say. So the most recent conditions once the forecast period starts. So we need a little bit of ERA5 data for that to represent the historical conditions. Then we're downloading the CS5 forecast data, which is a forecasting product for 8 or 9 months in the future. I forgot exactly, but it consists of 15 ensemble members as well, or 50 ensemble members, which we're all running through the hydrological model. Then we resample both of these data products onto the model grid to make sure the hydrological model can work with it. Then we're running the model. As I mentioned, it's WFlow, which is the hydrological model from Deltares. We first do this catch-up period where we use the ERA5 data to make sure that the model is run up until the period where the forecasting period starts, and then we can use those conditions to initialize the model for all the ensembles in the forecasting period, which is then the CS5 product. And once the model has been done running, we can plot the results, and we currently store them on a location which is a public facing HTML site as well. So you can look at the results just through your browser, which is pretty nice, I think. Just some example results of the workflow that we have currently running. We run it for the Rhine Basin. So for those of you who are familiar, you see here a small map of Europe, which in green where the Rhine Basin is located. It's one of the main river basins that flows into the Netherlands, where we are highly depending on the amount of water that's coming through within the Netherlands. This is a screenshot of the HTML page where we show all the results. And you see we produce a folder for every month. So every month there is new forecasting data available. And within this folder, we have the results from the model run, actually just figures from the model run. So I here look into the most recent one. So this is triggered last month. And then if you click on the figure, you get a result like this. So here you see the black line is the hindcasting period. So that's the ERA 5 data to make sure that we catch up until when the forecast starts. And then from that point onward, we have 15 ensemble runs. So 50 different hydrological simulations that provide the discharge time series here, which here presented as quantile ranges. So the colors indicate sort of the likelihood of where the discharge will go. And this will provide an overview of the discharge that's coming. And you see the further you go into the future, so the first couple of days, the lines are pretty close to each other, but the further you go into the future, the larger the spread will become of those runs. Just very shortly, the requirements for our workflow. So we currently require the user to update the model configuration, so the settings and the input of the model itself. So for example, for the Rhine, we uploaded the Rhine model configuration with the workflow as well once we started. We need access to the climate data store, so that's Copernicus, through the CDS API, that's a Python library, and then Slurming contract for the workflow. And then currently, at least how we set up the workflow now is that we also have a public facing HTML site to take a look at the results. So that was very briefly a summary of our workflow. There's a link to the GitHub repo, which is open as well. You can see the workflow results as I just showed in this slide as well when you follow this link. And if you're really interested, you can also take a look at the WFlow hydrological model GitHub repository. That's it. Any questions?
Thank you very much, Joost. Yeah, we have a question from Anne in the chat. Do you share data that you download, for example, the ERA 5 or the CIS5 forecast?
No, we don't share that data. We don't do any real processing of that data actually. So we just download it from Copernicus, which is open and available for everyone. We only just change the grid resolution mostly. So there's not too much stuff happening there. Hence we decided not to put effort into sharing this data directly. Hope this answers your question.
And would you say it's answered?
Or would you be interested in having those data?
Yes, but I mean, I thought this is an EOS project, so we are supposed to follow open science approach and principles. So I thought to avoid duplication of data and re-download of data, maybe what we download within the C-Scale project could be shared, but that was my point.
Right. Yeah. Yeah, it could be. Currently, we're downloading it only for the region of interest, so we're currently also only downloading it for the Rhine Basin, which is we can share it, but I don't really see a direct benefit of sharing it. Don't know if somebody else has different ideas about that, but
if I may comment, that is, and what you were suggesting is indeed the ambition of the C-Scale project, right? But it's not always possible to download and make every data set available for each specific use case. So in this particular example, we focus on ERA 5 and the seas forecast data from the climate data store. and those data are for a specific region for that model. So if there was a global archive available on the C-scale infrastructure, then we would have pulled it from there. But for the moment, it wasn't available. So we built functionality to make the data available on the infrastructure. And that's part of the C-scale ambition, is to make data available where it can. And if the data is not available, provide you with the resources and the tools to get the data that you need. I hope that answers your question.
Yeah, I mean, it does answer my question, but I just mean, I have the feeling many use cases are duplicating, and like ERA 5 are also of interest for many people. Maybe at some point it would be nice to have a available data set, maybe global and for C-scale or for EOSC more generally.
Yeah, I completely agree. Absolutely.
Yep. Thanks.
Okay, thanks. Very good point. I'm taking notes. Let's see if the providers agree. We can, of course, suggest. Then I think due to the time restrictions, and would you like to present before you leave at 10:30 now, or would you prefer to present when you are back at 11:30? I mean, it's up to you.
As you want.
Yeah, please.
I mean, someone else can also present. I don't think I'm the only one here. I think Tina is here. Jean is here. Okay, we can share.
Yeah, actually, the Pangeo is a collection of use cases. Are you going to present just one overview, or are you going to present each of them separately?
So we are going to present like the general approach of the Pangeo and list the different most of the use cases, but briefly.
Okay.
So, do you want to have it now, or?
Before you leave, maybe, yes, or are you presenting, or is Tina presenting?
I don't know. Tina, do you want to present?
Sorry, I have kids around and I prefer you present. Thank you.
Okay, let me share my screen and let's hope it works. Do you see something?
Yes, I do.
But then it's paused. I always have this problem that it's paused. Stop sharing. And I don't know why I always have problem when sharing. Just 1 minute. I need to put it not as big. Okay. And I will share a portion of my screen. So you should see now?
Yes, we see it.
Okay, so you see many names at the bottom here, and this is mostly all the different use cases. And what we want to mostly show is it's a collection of use cases, as Sebastian said, and this is to have an approach where we aim at being open, inclusive, and reproducible and scalable for Earth observation data analytics. So first, we want to show you a bit what is Pangeo, what kind of link we have in Europe with Pangeo and EOSC and the different use cases. So briefly to talk about Pangeo, this is a global community initiative for big geoscience data. It's an open community, so we have like a common vision. It's community-centric, and it's a collaborative culture. We are aiming at developing open platforms, so to have open user interface, scalable compute and data models, and open source software integration. And now we are working on open deployment, so from the laptop to cloud with EOSC and HPC. So we can see Pangeo as a platform, which is really scalable from the laptop to the cloud or HPC. And we have like a data model, a user interface, scalable compute, different resource management and storage system. And it's a bit cherry pick when you make your deployment. So we can make different types of deployment if you want to do a deployment of your on your laptop, on an HPC, or on a cloud. And this is a bit what we are trying to experiment in the C-Scale project, is to have maybe different types of deployment and serve different use cases. So each of the deployments, so we will have one deployment where we want to have Julia. We have other deployment where we are using Python and Dask. We can have deployment on the HPC. But the interface from a user point of view is always the same. So here in EOS, we aim having integrated different components, and in the C-Scale, what we are adding is, what we are aiming at having is to have more data access. So one of the constraints we have is that you can have easily on EOS compute, but it's more difficult to have data close to the compute. So these are the different use cases. And as we said, it's a collection of use cases. So we have one use case, which is called Pangeo Climate, one other, which is called Greenest, one is Reliance, Biologging, Julia, and Training. And I will not say anything about the training, because the training is any one of the above. So each of them can correspond to different deployments. The training is what we use when we are training a large number of students, for instance, like between 20 or 100 students. And so we need to have sufficient resources, but they are the same kind of deployments. So this Pangeo Climate, this is mostly for the Nordic Earth System Modeling Hub and the Clever community. And we work with climate data. So we work mostly with SEMIP6 data, which one part is already on the cloud on AWS, but many of the data we need for Clever, for Arctic, is not available. And the goal is to exploit this data in conjunction with other data sets like observation. And this is to address scientific questions about the past, present, and future Arctic climate system. We want to adopt open science practices and to share experience about EOSC. So we want, for instance, to produce ZAR for data that is not available already for SEMIP6. We want also to generate a stack data, stack catalog, for instance, also for observation. And we want to develop a fully reproducible and reusable user Jupyter notebooks. And typically we want to follow best practices. For instance, following what is done in the Environmental Data Science book, which is an initiative led by the Alan Turing Institute. So this is not my use case, but this is a Greenest use case. I don't know if, I don't think Lorenzo is here. And they are using Copernicus Global Land Service. And the goal of this use case, I think, is to reprocess and to make better product. So this is typically what is shown here from the data. They want to generate some data cube and then use the Pangeo software stack to make some Greenest map. So this is the specific project. This Pangeo Reliance use case, this is about Arctic running, and it uses different types of data sets, so like Copernicus Global Land Cover, ESA World Land Cover, and ERA 5 land data. So this is not the ERA 5 data we have seen before. And here we are aiming at using Pangeo ML, so machine learning, for deriving maps where we can show a loss we want to forecast the moss and lichen cover to see where eventually we have some loss of this type of vegetation. Sorry, this is not started yet. I don't know, Felix, you're here? If you want to explain this use case.
Yes, I'm here.
Okay, you can.
Yeah, so the idea is to do deforestation mapping with Sentinel-1 data by using the whole time series information, comparing. So on the left is a recurrence plot of different pixels for deforestation and non-deforested, and on the right you see a map of, okay, how do this look spatially. And we showed that this seems to work on a very small example area, and now we want to scale this up to larger areas. One area of interest would be central Germany, because we have a lot of deforestation or forest disturbance at the moment there. And then also another use case would be Yucatan. And we're currently waiting for the access of the Sentinel already pre-processed Sentinel-1 data by the TOWeen on the EODC clusters. And another idea behind this use case is to test the scalability of the Julia data cubes packages that we are developing for the access of large data, and also to test, okay, how good does the scale on the cloud, and how can we integrate this into the Pangeo ecosystem as well. That's it.
Okay. So I think at some point we were asked if we had some issue to share, or if there were things we wanted to share. So so this is the first experience we have with this scale, and the fact we have different infrastructure with different setup, it makes it more complicated. Maybe in the future it will be easier for making different deployment, but this is an obstacle so far. Access to necessary data set is not always facilitated by the C-scale infrastructure, because we don't fully understand where the data is and how we can access to data and which data we can access. It would be easier for us to have like one set of like one Kubernetes cluster, and we could have all the different use cases with different kernels. So for HPC to uniformize the setup, uniformize, I think this is what Lorenzo, to have like a more streamlined setup could help, but we would need to have collaboration with HPC system admins to optimize the usage. So it means this is a bit isolated in terms of work we can do. And last but not least, we found it's very difficult to have like a open science and fair data approach. We don't fully understand how in C-scale we need to fit or work to have like fair data and open science practices. And that's it. If you want to know more about Pangeo, you can have this information, which will be in the slides. Thank you.
Okay, thank you, Anne. We're taking notes about the feedback. Andres, do you want to ask a question?
Yeah, just a quick question to educate myself again. The Pangeo Julia use case using Sentinel-1. Do you use a Sentinel-1 preprocessing also in Julia, or use some common Sentinel-1 preprocessing tools?
For now, I wanted to use the already so there's a preprocessed Sentinel-1 data stack available on EODC, and
Okay.
we asked for access to that. Currently, I know that there are developments of doing also sub-processing in Julia, but that is not on the stage yet where it's fully usable.
Yeah, thank you.
Yeah.
Okay, thank you. Lorenz?
Yeah, I was triggered by the fair data comments, that actually it's a good idea to also maybe have metadata templates for the final products. Our software has its own rules to provide metadata in the netcdf file, but when we wrote our post-processing scripts, I don't even know what kind of metadata we put there. And that's another thing that it's not discoverable at this point. But to have a discussion and maybe a standard format to say, okay, this is this use case produced by this institute, things like that. If it's not available yet, then it is helpful.
Yeah, it would be very helpful also to see what other try to achieve in terms of fair data and open science practices. Thanks.
Yeah.
I don't see questions yet, but please feel free to use the chat as well if some other question came up after the presentation. Thank you, Herb, for the presentation. Very nice.
Thank you.
Let's then move on to the following one. I think another use case with time constraints was a Grapevine from Itainova. So is Francisco around? And would you like to present now?
Okay, I will try to do my best. And try to share my screen.
Okay.
So I think now you're able to see the screen.
I see the presenters mode.
Okay, now better.
Yes, perfect. No,
Okay.
that's perfect.
Well, just a brief introduction to the Innovate and Spanish Research Center. We are more focused in the innovation than in the pure research. And here we are going to talk, I am going to talk about the Grapevine project, which is the use case that we want to improve using the 3-scale capabilities. Well, our goal within this project is to create models, prediction models of the phenology and the risks of pests within the grapevines. Why? Because it is a way to improve the sustainability of the farming, in this case, of the grapevines. Well, just for making you a bit more clear, we are working with data of villagers, which are part of 3 denomination of origin in Aragon, which is a region in northwest of Spain. We are taking data from Campo de Borja and Cartagena. In this slide, you can also see which is the distribution of the climatic extremes, and in the right, which are the distribution of the different control parcels, which are using for providing data about the phenology and about the presence of pests. Okay, well, this is a high level view of which is the current status of the data flow. Well, we are considering data or the FARA, which is providing us with the data of the parcel. That is the physical location, and then also about the phenology and the risks and the presence of pests through the different seasons. We have data from since 2009, as we have to use Sentinel-2 images, we restrict the data since 2016. We also use data from the Spanish registry of cadastral parcels, because there we can obtain the polygon and the geographical definition of the parcels we are considering. As I said, we are using Copernicus data in order to obtain the digital index, in this case the NDVI index, for describing which is the evolution of the parcels through the one of the issues that we have to solve during the project. You have to use this data because the resolution of the Copernicus images, it is 10 meters per 10 square meter per pixel, and there are a lot of use of this data for variable cultivation, but for good crops, like we are using in this project. We also use the climatic data provided by different station network. Use IMET, which is the Spanish meteorological agency. We also use the CR network, which is the network in which is used by the Spanish irrigation system, and we also use some Grapevine climatic stations which are deployed during the project. We also use ERA5 data when we lost the data for a station for a very long period of time. In this regard, what we use is only the data of the stations which are providing data for more than the 90% of the date of the days in a given season, and also they provide more than 90% of the sample data, considering the sample frequency of each of the stations. Finally, we use for making the forecast. Well, the predictions, the forecast provided by Aqua, is one of the partners of the project, and also we use the one which is provided by Pangeo when we have some fails in the models of our apps. What we do? Well, basically, first we process the data, we download the images, we normalize the data, and in the case of the Copernicus images, what we do is to cut the part of the images which is related with the cadastral parcels. We also calculate different vegetal index using the data, which are what we can say are the classical way of making the prediction about the phenological evolution of the in this case of the vineyards, but also of the evolution of the risks. We merge all this data, considering in this case that the climatic data is considered at the station level, and in this case what we are making is to use the data of the station closest to a given parcel. Okay, and that's how we obtain the data for training the models, for creating the models about the phenology and about for the different diseases. Sorry, yes. There are two modes, which are viral and lobesia, and two fungus, which are oidium. And then, these models are training and presented as REST API services for being used by the let's say the graphical application which provide the capability, these capabilities to the final users, to the farmers. We use Jupyter, Python, and different libraries for making the models, and we provide them as API. What we want to do in this experiment, we would like to take the advantage of the capabilities provided by CScale for accessing Copernicus and ERA5 data. And what we are going to try is to test if using ERA5 data is possible to obtain better predictions at the parcel levels. In this case, what we are going to do is using ERA5 estimations for creating the vegetal index and all other derivative indexes from climatic data, but instead of replacing the fails in the climatic station, what we are going to do is to replace, you know, that ERA5 data is provided with Adelaide. In this case, what we are going to use is the climatic station data for saving this gap in order to provide the predictions, taking the forecast for the long as long as it is available. And well, we are going to use the CScale resources for making this. And sorry, because we didn't start the deployment, we are solving some issues with the data, and we want to deploy this directly on the existing infrastructure, taking advantage of the capabilities of the platform as a service. Sorry for my voice, I am living sick.
Thank you for making the effort, Francisco. We really appreciate it. I hope you get well very soon. Yeah, we will be waiting for you to proceed with the deployment. No problem. Is there any question from the audience for Francisco? I think Andres, you have a question.
Yes, just out of curiosity, do you somehow address the smoke taint problem on grapes as well? Because I've seen some vineyards struggling with it.
Sorry, which one?
Smoke taint, or the wildfire smoke, which can affect the quality of grapes, and there is no good sources for it.
Yeah, well, the issue is that we consider this pest because they are present in the in the region of providing the data. But we also work with another thesis in Greece, and our propose is to extend these models to other pests and to other areas, and to other also ones that we know how to proceed also to other woody crops. Currently, we are working with the Aragonese government in the station to these models to these to apples trees, and also to peach trees, and also, considering the pests that are affecting them. If we have data, I mean field data about these pests, we can consider to train for another pest. And obviously, using ERA5 models, I think we can extend these models to any place around the world, because we are not depending on the climatic station networks for having this data about the fields. I don't know if I answered your question.
Yeah, more or less, yes. Thank you.
Any other question? Okay.
Okay, thank you.
Thank you.
See a question in the chat. So I propose we take a small break. It's almost 11 o'clock. Let's break for 15 minutes, and then come back to present the remaining use cases. So I'll leave everything connected here, and I'll hope to see you in 15 minutes. So talk to you in a few minutes. Thank you.
Bye.
Bye-bye. Hi, everyone. I hope you are back. I pasted in the chat the list with estimated times for the remaining use cases. Hopefully, you guys can make it in 10 minutes, so we stick to the scheduled time. Next one will be return. This is one of the native use cases that's been running longer in the infrastructure. So, Milutin, please go ahead and share your screen. I cannot hear you. Not yet. No.
Do you hear me now, maybe?
Yes, now yes. Perfect.
Great. Relief. Okay, I will share my screen.
Mm-hmm.
And let me see. So do you see my presentation in presentation mode?
Yes.
Great. Yeah, a return use case. It's about monitoring Amazon rainforest recovery capacity with Sentinel-1 data on EUC infrastructure. So this is the use case, and those are my collaborators. So a long list of people, yeah, from yeah. So let's because of the shortage of the time, let's move directly to the use case itself. Yeah, it's about processing the whole Amazon basin, processing Sentinel-1 data time series of 4 years of data on for each pixel 20 by 20 meters. This comes in total about more than 18 billion pixels, and we've done some calculations because we are just about to do the upscaling. Probably next week we will do this. So it would need about approximately 500,000 CPU hours and more than 40 days of computation. Yeah. And the reason why we are doing this is because we would like to track disturbance and recovery patterns of the Sentinel-1 radar signal in the Amazon rainforest. So here you can see the a classical time series. We introduced a certain model where we have some history period and monitoring, and based on the history period and some statistics, we derive the confidence intervals, and basically we track when the signal leaves the confidence interval, and then we derive a bunch of features and of these disturbed signals, and ideally at the end we would like to derive some statistical analysis of how long those signals takes to recover, and many other aspects of that process. Yeah, for the implementation itself, we rely on the Sentinel-1 data that are provided by EUDC, and we rely on SURF infrastructure. So we done a data transfer from EUDC to SURF, and then on SURF we developed, we also onboard our own Python code where we are building the data cubes, and from some extra Python code to do statistical analysis, visualization of the time series, and mapping as well of the disturbances detected. Yeah, and we also use Slurm for upscaling the code on HPC. Those are some preliminary results. Yes, as you can see, we had to split the area on different tiles, and just to optimize our jobs, the duration of the jobs, and also distribution on the cluster. Those are some time series, some disturbances. So there are just different type of disturbances, and here you can see this typical pattern of disturbance we can observe and expect in Amazon rainforest. And here is some statistics of that basically some of the features we derive are also there is functional relationship between them, and we are planning to explore this further in a scientific publication. Beside the features, we also derive some annual statistics of the time series, and then here you can see how this annual statistics looks like for some disturbed area. Yeah, this is yeah, sorry, this is a total statistics. Yeah, my apologies. So different total statistics of the 4 years, and then we on top of that we have some annual statistics where we can track how certain areas are changing the signatures from year to year. Yeah, and eventually we also use some relation of the statistics with other parameters such as forest age and other covariates, and yeah. So that's all about the use case, and we are planning to to prepare a scientific publication on that in the future. And of course, as soon as we submit and the publication is accepted, all the products and the code we developed in this use case will be freely available. Yeah.
Great. Thank you very much. That's very good. Any question from the audience for Milutin? Okay. I don't see any. Just to mention that most of the use cases have been using cloud resources, but Milutin is one of them, using as well HPC at SUR. So just to give you a sense that everybody's running on the same infrastructure in scale. I think was there a commonality here with the biocarbon use case? I think at some point.
We were discussing a bit along those lines, so that would be interesting, because the idea is also to replicate this workflow now on EUDC infrastructure, and we would like to do this also not only on South America but also on Africa data. Yeah, and that could be an interesting collaboration point as well. So because I can share my results of this disturbance detection for Africa, and we can also see how we can collaborate on that.
Okay, great, thank you. Yeah, we'll have the biocarbon presentation later, so we can also discuss them.
Perfect. Yeah.
Thank you very much, Milutin. Next on the list will be TUB. They have two use cases, the wetland water stress analysis and the GPET. I don't know if you are going to present both at the same time, or you prefer to split them. So is that, Matthias, I guess.
Hello. Do you hear us?
Yes.
I would have.
Oh, it breaks up a little bit, the audio.
We just changed our seats. Yeah.
Okay.
So because there's some overlap between WS and GPET.
Sure.
I'll keep myself as brief as possible, and I'll start off with US, where we do the wetland detection. So building on top of some of the research we did here by the TUB, by Bernhard Marshallinger, we use the Sentinel Sigma Naught data with where we derive a harmonic model which captures the dynamic of the signal, and with it we hope to detect the wetlands. There was also done some further analysis by a colleague of mine, Florian Roth, who showed that when you derive phase and amplitude from these harmonic parameters, you can kind of already see or interpret by visual inspection the wetlands, as I see here on the right, around the Neusiedler See in Burgenland in Austria. And so our goal is kind of to develop a classification model based on these harmonic parameters. And we also want to improve maybe by using tailored bases, and there are some stretch goals. However, since we are in the last 6 months, I probably have to drop some of my darlings there. But more on that later. So we started out with random forest classification, thanks to knowledge from Matthias and his experience, because I haven't never used that before. We found we got some results, especially kind of for detecting which of the harmonic model parameters are important and which are not for detection. However, it became clear quickly that the random forest, that we need more spatial information to do a reliable detection, because the random forest detection is really very noisy. So what we are now at the moment is using a machine learning unit or a residual unit, which one of them doesn't really much matter, to do this classification. So the approach is, I have more experience with this computer vision unit types of things, is to do something similar that I did when I was still working at AIT, where to get reliable detections with the unit, we want to make it as easy as possible for the machine learning algorithm to do to detect wetlands by pre-processing the data, capturing all the dynamic information and condensing it as much as possible. And here we thought about, because it's already visually perceivable when we use this phase amplitude and median, that we use this as an input. Because if we do things like this, we want to segment based on physical parameters that we do not exactly know. Data augmentation approaches that are often used for object detection do not really work for CNNs here, because you kind of just overfit it. It works when you do moving or rotation, because your objects often differently rotated or moved. But here we look directly on dynamic input raw data, where we try to find statistics within. So here, at least this was also that we showed as well in what we published at AIT, is it's really more beneficial to pre-process the data to get as close as possible to the solution before feeding it into the classifier, the machine learning classifier. So during this, we developed a pipeline for doing this segmentation classification using a unit classifier, which I will show later in the next slide. And we already did some tests on the Cloudflare backend for this, using their GPU device to run, I think, 100K training sample, which already worked quite well. However, I still need to do validations. And if this is turns out to be not enough, there are still some ideas to integrate the knowledge we've gained from the random forest experiments at EUDC, and maybe add the dominant features from the random forest classifier to the input for the unit to further improve these results. Also, we were thinking about using, now that the Stack API is available at Cloudflare, to derive something from the sigma gamma data that they provide, and maybe use SVD components or tailored basis as an input. However, let's see, those now stretch goals. But if we have time, it would be very interesting if we can improve. Yeah, here is quickly some of the challenges that we encountered that we are now implementing. We want to implement this machine learning workflow for units, and therefore the random forest that's already there, to be able to use this also in different projects and kind of have an open protocol, so to speak. And one of the main issues with, if you want to feed your raster data into a machine learning model, is of course to deal with the nouns. Currently, yeah, I just never sample them and just mask them later. But of course, we could know yet which one's the preferred way. It probably depends on application, but that makes the pipeline more complex. Is either replacing the nouns with medians or averages, or just defining a non-classification target. Also, balanced sampling. This is actually one of the major issues right now. I mean, it's kind of working, but it's really slow. I'm not fully utilizing the GPU at the moment, because it's really hard for me to get task lazy loading and streaming to kind of connect the two of them, so I can stream in the data chunks while the GPU is training batches. I have a hand-rolled solution for this at the moment. However, I might be curious to see if there's a task ML implementation, if that's already does what I need. I need to look into this. And yeah, there's of course also issues with projections and overlap. Luckily, we currently the harmonic parameters are in Equi7 grid, so overlapping is not that big of an issue. However, again, how do you deal with borders, and how do you load the chunks in a way that is efficient, so you can do a halo around your tile, and when you do the inference with your model, things like that. So this is the current implementation we have, where we go from the left, from the X-ray task world to the PyTorch world, which is in orange, and then into the SciPy scikit-learn interface on the right. So this is what we've implemented at the moment, where kind of we sample from the backscatter data, put everything into an X-ray task SAR format. And this is also where we do the data cleaning and the pre-processing, like calculating the phase and amplitudes and preparing the data as good as possible for the net. And in the next step, that's where the patch sampling and the balanced sampling and the non-handling happens. This kind of the moment happens on the fly, and we developed a protocol called EO transform for this, to be able to do this in a streamed fashion, which I will get into when I talk about the GPAT workflow, because there it's relevant as well. However, once we stream this in, we kind of wrap this then in this iterable dataset interface from PyTorch, so we kind of can put this into the PyTorch world and into the data loader from PyTorch, and then there we train again our neural network estimator. So this is where we are right now. This is currently implemented. What's missing in features at the moment here is to do inference over large areas, and doing kind of, because you need to handle the borders properly, and you still need to think about how to best approach this. Which brings me neatly along to the GPAT project. Here we want to kind of do a comparison between our current algorithms based on CPU, and if they're better or can be more efficiently calculated on the GPU. And there are a few algorithms we want to look at, resampling from coarse to fine to coarse resolutions, and statistical averages and things like that. But here we have, the requirements are mostly already there. So thanks to Sebastian and the others for providing us with all the data and the devices and the environment we need. We can start on. The only thing I currently are looking for is a good profiler for Python, and for those pipeline, kind of how to figure out where my bottlenecks are. If I want to do a fair comparison, currently looking into PySpy. I don't know if anyone has experience with it, but it's written in everyone's current favorite language, Rust. It's a sampling profiler for Python. Seems to be interesting for this kind of work. So here's the EO transform protocol workflow, which I now also want to use for the CUDA training for the wetland. Because here in PyTorch, I'm already on a GPU device, and I have this streaming problem as well, where the sampling takes so long, while in the meantime, I want to train the model. And so we have to similar issues with many of our algorithms, where we waiting for IO or data cleanup to finish. So this is where this protocol comes into place. So we have an interface that's an input source, a transformer that takes the input source and chains transformations. As long as they follow the right protocol, they can be kind of daisy chained together. And at the end, there is a sync, and the stream process handles the interleaving or the IO hiding. Because currently with Task does nicely do the lazy loading, but there are certain problems that we encountered when developing our workflow, especially for the wetlands, is that kind of the rechunking of the large data set takes them more time again than if I would just be able to load one TIFF file at a time and process this in this manner. So it gives a bit more flexibility, but of course it involves a lot more coding. The way it works is the source kind of provides does the IO, and as you can see below, this is the processing graph. So we kind of hide the input and the output writing between the processing steps. And this gives us a huge boost in performance. Yeah, and for GPAD in general, for water wetland, we already work with PyTorch to do the training, but for our more down-to-earth algorithms, or not machine learning-based algorithms, we need something different. And there's checks, which I looked into it briefly by Google, which is a graph-based CUDA pipeline, but I don't know. The thing is with Google frameworks, it's often sometimes they're dropped suddenly, and then you rely on it, and then you have nothing. Then there is Numba, which I'm currently favoring this one because it's a one-to-one translation of the CUDA API, and I don't need to pre-compile everything, which would be just using CUDA and write your own C bindings. But this is a little more easy to maintain. I don't have to write the overhead of C bindings. I don't need to create a continuous integration pipeline to build for different platforms and things like that. So I probably would start out with this one. Yeah. And yeah, these are the links to the protocol I just mentioned that I use in the machine learning workflow, as well as the GPAD workflow, which the EO transform is the basic one, and EO transform Xarray integrates Xarray and task in a meaningful way. Yeah, that's it.
Thank you, Bernhard. Very interesting. Yeah. I may have a look and see if I can find a good Python profile for you. Maybe I can help as well.
Sorry? What the Python?
The profiler, a profiler for comparing the performance for the workflows.
The PySpy seems to be pretty good.
Okay.
But I'm happy for any other suggestions. I have only looked briefly at it because the one that the C profile that comes natively with Python is not really. It's great if you work just in Python, but as soon as you go into CUDA or any C libraries, you don't get any information. And it also profiles all the workers of all the threads, and you can kind of nicely line them up and produce speed scope graphs and things like that. So there's some, but if I'm happy for all suggestions. So if you have an even better, a good one, then please let me know. It would be very helpful.
We'll have a look. Thank you. Any other question for Bernhard? Okay, if not, thank you again for the nice presentation. So those are two use cases in one presentation, so we save a bit of time. Thank you. Next on my list would be Sal on the fly from Guido. If Guido is around and is able to present.
Yes, I'm here.
Okay, thank you.
I need to share.
Mm-hmm.
Share what exactly? Wait a minute. Wait, I'll have to open this. Share. How does this work again? Share screen. Okay. This one. You see this?
Yes.
Okay. So the project is called SAR on the fly, and it actually means SAR analysis ready on the fly. So that is the key use case, more or less. So what we're trying to do is, especially in the case of Sentinel-1, there's no consistent production of application analysis ready. I mean, sometimes we call it application ready data. So that is a big issue. And there's two things. One of them, it's relatively slow on a CPU. And especially for things like interferometric processing, it is, say, relatively expensive in terms of CPU. So the main aim of the project is to demonstrate GPU-enabled SAR processing, and with the of course to speed up processing. That's the key point. But also then to show why it is so important to have ARD available for analysis, and that's of course a bit more generic problem. But I think, personally, I think that a lot of attention is spent on Sentinel-2 with level 2 and level 3 and whatever, while this is not the case for Sentinel-1, and that's, I think, a huge problem, because of course we have a huge archive of Sentinel-1 data that is that remains to the large extent unexploited. Okay, what we do is we make coherence specifically because it is in agricultural context. We're doing crop area monitoring, and we do that in Ukraine. So that's that was say in a way a coincidence that when we started, we needed to define an AOI, and where this information is at the moment most urgently needed is not so much in the EU, but in Ukraine. And we have been using that to a very good results. So at the same time, there is an initiative started by Cloudfaro, Creodias, to support Ukrainian researchers with access to cloud, but also access to data, especially again application-ready data. So we have basically piggybacked on that initiative to make sure that the data is openly available. So that also means, by the way, that there is a sync with Google Earth Engine. So the data is both openly available on this EO4UA platform, and as an extension, I mean, as a logical extension, if you want, you can also find it on Google Earth Engine. It's all described in a Medium post. There's a link here that that you can check out when you get the slides. Why is coherence so interesting, especially for agriculture? Very quickly, coherence shows change at the surface. Change at the surface means a farmer is doing something to the surface, or some crop is growing or being harvested, etc. And if you combine that in a time series, you can then see what's going on. Progress of the season, what kind of expectation of the crop types there. And you see here, this is a simple RGB composite of 3 dates, 3 consecutive dates that show this. Just to mention, we had, of course, Sentinel-1A and 1B until the end of 2021. It is highly required to have both, but you know, we cannot do anything about sensors that fall out of the sky, more or less. So what we are doing, we are doing our best to work with 12-day coherence, but it would have been much better if we would have 6-day coherence. And then the other thing is that we also have at least, okay, so if we only have 12-day coherence, it would be very nice if that is supplied at the you know, without gaps, and that's another issue. Okay, this is a sideline. Has nothing to do with C-scale. So what are we doing? So here is basically, this shows all the frames that you need to process per orbit. So they contain also a number of different UTM projections. We work with local UTM projection, the same as the Sentinel-2. So you see here, okay, this is an update until September 22. We're now further than that. We're about 4,500 images, and so this is going into a float coherence that is then pushed to the Samba share, and also then to the Google bucket for ingestion into GGE. And we also have a GeoJSON metadata catalog. So we have actually looked at stack, but we found it rather a bit bloated, if you want. So you had to do, you know, the real key metadata that is specific to this particular coherence data you can capture in a GeoJSON, and that's of course pushed out with the same data. The EO4UA initiative has a viewer. It has access to different what we call card types. So Copernicus analysis ready data, which is the usual Sentinel-2 things, stuff from Sentinel Hub, but also daily gamma and also this coherence. So that's that you can actually visualize. This is the background here is actually a coherence scene. Again, the link is there. You can try it out when you get the slides. How are we doing this? So we are using an existing open source software called ALIS, done by CGI Estonia with the support of ESA. So this is basically an integral implementation of the Snap toolbox on a GPU. And then you can deploy it on your local GPU. But since you want to handle full scenes, it's better to use a beefier kind of GPU, which are available on Cloudflare. And the good thing is, of course, on Cloudflare, all the SLC data is already available in the S3 archive. So there's no need for data transfer if you work on the Cloudflare platform. So we are using a VMA. Okay, this doesn't mean much maybe, but it's basically a very fast GPU with 56 gigabytes of RAM on board, which means you can actually transfer full scenes on board. We don't do that because, of course, processing is actually done in subswath, so the actual size is a bit smaller. That is processed at the same time. And what is interesting, I mean, this is actually the page on challenges. So, of course, the implementation, the configuration is a challenge, but in this case, a GPU is expensive. It's a €2 per hour resource. So it's of course very important that since we do the processing in regular bursts, that we switch the machine off. And you need to do this by doing unshelving. And in the beginning of our project, that didn't work for GPUs. So Cloudflare had to do quite a bit of an effort to make sure that the OpenStack unshelving worked correctly. So we basically unshelved it and then lost it. So that was an issue, of course. You don't want that. And but now we routinely shelve at the end of the process and unshelve when we have a new batch run that then runs for a couple of hours. And of course, this way you manage resource. And that's very important, I think, overall in the cloud, is that you have to be very careful about how much resources you use, and be pretty smart about starting it up and switching them off. At the moment, we still run batches sort of manually, but they can be cron tapped. That is, of course, a point. There is some configuration that is still unfortunately manual, but that's just a matter of it's not fully operational. It's like it's still a demonstration case. Now, what is important is that when you use GPUs, you can reduce the coherence processing time to about 2 minutes for a full scene, and that compares to, well, I mean, there's of course different configurations of Snap, but it's about a factor 15 quicker. But the problem is then that you run into the latency. So you know that if you have your data on S3, it is not as quickly accessible if you have it on your local SSD or special this NVMe and stuff, whatever. So there is a considerable overhead in moving the data from the archive to your disk for processing, maybe to your memory for processing, if that could be done in one go. And it's actually in the same order of magnitude, so also about 2 minutes for the on Cloudflare. So this is, of course, where you can optimize. So we have been looking into various smart ways to cache data, so to pre-copy data to disk so that it is available the moment the GPU would run. But the problem is the GPU is actually so fast that even if it uses 2 minutes, it's still waiting for data most of the time. So also memory loads, etc., are the bottleneck. So, but still, we managed to process at least 25 coherence scenes in an hour, and that's really good. So that is good enough to do daily loads over an area like Ukraine in an hour per day or something like that. So, but there again, so that was one of the objectives actually of the C-Scale request, was to get more insight into how you can, what kind of tricks are available to do this caching. Of course, you can run on parallel machines, but then of course you need a GPU on each of them, and that of course blows up the cost. But if you have any ideas in that direction, then we're happy to use and discuss those. What is also interesting is that so ALIS is it's open source, and you can have of course, if you're a CUDA expert, you can actually check out what they're doing. But there are also quite a few more generic tasks that we're now looking into. So things like doing indexing, doing extractions, group reductions, things like that, which are now becoming available. It was mentioned before. So how well is this programmable? This particular kit, the Rapids-I, which also is available as a Docker with a QSIM modules, which is basically the SkyKit image package on CUDA. And they have lots of interesting routines that you can use directly on a GPU. The issue is always, of course, you have to keep the GPU busy on computing. Overall success. So we are now using this since basically operational means that we have sorted out all the issues, and then and we now do a routine generation of this data. Already said it is factor 15 quicker. We have everything from September 2020 till now, because we're comparing seasons as well. That is about 4,500 coherence images, which needs about 40 terabyte of input of single loop complex data. We are already, of course, integrating that in our analysis work and producing crop maps, crop status, crop events, all the sort of information that we're interested in this Ukrainian analysis context. It's of course fully deployable in other areas. So if you would have another area of interest, of course, Ukraine is quite large. It has these many frames, but you can do this very easily on a more limited area, and that's just simply by scripting around this ALIS software, and that's not difficult. What is also interesting is, of course, that the ALIS group is part of our project, and we discuss regularly on how the open source is going, where it is going to, what would we features to have, etc. So this has now led to continued funding by ESA, and that means that this open source will continuously improve. So what is the final product? So in the end, of course, what we're hoping at is that this is indeed a scalable service. So and we know that this is mostly in the hands of CGI. They're talking to Cloudflare to put this on the new Copernicus data space ecosystem. So this is the single follow-up of all the DIASys. So everything is moving now to a single platform. And that is, of course, a huge development. It's very important. And, you know, what will happen in the next years is that a lot of stuff will consolidate on this platform. Since it is a stable platform that will be available for the next 6 to 10 years, we're likely to get much more focus on service supply. So people doing processing as a service, software as a service, etc. So that is a major development where I think some of the C-scale experience is quite relevant. I mean, I've seen all the presentations that doing all things that eventually should, of course, collate on this system. So, of course, GPU acceleration is generic, and I find it very it's not widely used in remote sensing at all, Earth observation at all. It's surprisingly because there's lots of scope there, atmospheric correction, biophysical parameter generation, blah, blah, blah. Everything is in principle GPU, parallel. So, many of those processes are local, so should be able to be accelerated considerably. We are still, of course, very much focused on the EO4UA project, and in the course of our C-scale project, we have been able to help our Ukrainian partners to get OCR funding. So, in a way, the continuation of this production is guaranteed because we have funding to do that. And but eventually, of course, we would like to see it as a standard offering on the platform. And you have, of course, single GPU accelerated steps, but you can now start to consider doing this also in the workflows. And that's actually the on-the-fly part. So one of the key ideas was that if you can do this kind of processing sufficiently fast, why store the data? So that is also a Google Earth Engine concept. Do not store data that you can compute. So this is, of course, a particular pattern, but it's quite an important pattern because at the moment we are generating loads of global products, while you could ask yourself whether that could not be done on an on-the-fly, in an on-the-fly fashion. So, but that's maybe something for discussion. But yeah, we are very happy about the C-scale support. It has, it's a bit of a niche thing, this of course, but it shows that you can do very practical stuff very quickly. I think that, we more or less knew already that we are going to go towards this consolidation in the EO platform, compute platform in Europe. So that means that it was always a good choice to be on Cloudflare, and we have never regretted that. So that's something, yeah, also very interesting for us. Okay, that's, I think, the end of it.
Okay, thank you. Very interesting. Andres?
Yeah, just a quick question. You said that one scene processing for coherence takes 2 minutes. So by one scene, you mean the one .save file one area basically, or something smaller?
No, that's indeed the one save. So say technically an SLC scene is split in 3 swaths, sub-swath. But when I say 2 minutes, I process all 3 sub-swaths and merge them into a single output product for the whole. Well, I think in Sentinel-1 it's a frame, but you could.
And that's at 10-meter resolution, or?
Yes, that's at 10-meter resolution. No, okay. Sorry. No. We do 20-meter resolution.
Okay. That maybe explains.
But of course, the input is the full resolution. But, in principle, it's easy to do 10 meters. I don't think that makes a big difference. But we do this upsampling because you have less noise in your coherence.
Yeah. Thank you.
Okay, thank you. Unless there is any other burning question, I think we need to move on.
Maybe could you post the link to the ALO open source project, because I would be interested, and I didn't find it with a quick Google search.
You mean the ALOS?
Yeah.
I'll put it in the chat. Yeah,
that would be great. Thanks very much.
Okay.
Thank you. Okay, good. So next on my list is a Spotlight from Synergies. Hi, Dick.
Hi. I will share my screen. Can you see it in full screen mode?
Yeah, that's working perfectly. Thank you.
Okay. Yeah, our C-scale use case is called Spotlight, Semantic Data Cubes on Demand, and I will shortly explain what a semantic data cube is, what we developed here, and what should be the aim of the C-scale project. Our approach is to make the usage of Earth observation, big observation data a bit easier. Cloud-based analysis of terabytes of data with quite much more easier and maybe also programming free semantic queries. We also want to create and upscale our own developed analysis methods and not rely on the big providers here. So we have more a generic focus, not an application-centered one. I will show some of applications which are possible, but in principle, it's a generic approach. We are a quite small team here at the University of Salzburg, and therefore also C-scale resources help us to really show that we can scale such things to a more impact-related size. What we defined as a semantic data cube is what you see here. So it works at the moment on optical data. They should be calibrated at least to top of atmosphere reflectance values. We enrich every pixel in our data cube semantically, so there is a spectral category for each pixel available. We store or index the things in a data cube using data cube technology, and we created a web-based inference engine where we also programmed a Python semantic query language which can deal with that semantic data. What do we mean by semantic enrichment? That could be basically anything, but it should be a categorical value. In our case, it's a spectral category. We use for that a tool called Satellite Image Automated Mapper, programmed by our colleague Andrea Beraldi. But in principle, you could also use whatever. If there's once a nice developed deep learning model for enriching or categorizing Sentinel-2 data, that could be used as well. At the moment, we use this one. That's a fully automated spectral categorizer, which is based on a physical model. So we need no parameters, no training data. So we can really upscale that, parallelize that for whatever thousands or more data sets quite fast. We do that in Docker containers, and that works quite well. It's always beyond the land cover classification, to make that clear here. Higher semantic information comes then through querying through time with the data set. That looks like this, for example. Yeah? So that's such a categorization. It works on a pixel basis, so it's not very much sophisticated, but we can differentiate classes like very high vegetation, very high intensive vegetation, water classes, weak vegetation, bare soil classes, and so on, that can be used in our queries. We use data cube technology here to get away from the physical data structures, as some others of you as well. But in our definition, a semantic EO data cube, it's also published. You see the link on the lower left. We define that as a data cube where for each observation at least one nominal, that means categorical interpretation, is available and can be queried in the same instance. We use Open Data Cube in our implementation, but we have also some master thesis doing the same approach with Rasterman, for example. So that's no limitation here. What we have then developed is that inference engine for these semantic queries. That's a web interface like you see here, where you can access, and I will come to that because that's especially the C-scale Spotlight project here. You can use that generically for different fact bases or data cubes. You see below a data cube for Austria. That's our main implementation. We have one for northwestern Syria, Afghanistan, and the Alpine area with different data. So that's a generic web interface, and here people can do these queries. That is Blockly. Behind that, we have JSON-based queries, which are translated into data cube queries using that semantic language we developed. You see the GitHub link on the left, Semantic, which translates the queries into data cube queries and can deal with the semantic enrichments. So we try to give users access, programming free access. You can also use Jupyter notebooks for doing that, or command lines. That's clear, but to get also users access to make these queries with that interactive Blockly-like component where you can drag and drop your queries as you want, and you can share that between users and data cubes. Okay, that's our main implementation for Austria. That works quite well now. We have all Sentinel-2 data semantically enriched here, and that is used for different application cases. Some I will mention in half a minute to stay in time. I will not go too much in the architecture. It's all architecture. It's all published. Again, lower left. We will share the slides. So it's scalable, container-based. Concurrent multi-user access, multi-client supported through an API, and so on and so forth. So for example, the query on the right gives you, this small Blockly model gives you, for example, a national-wide information layer about how green is Austria. You see on the left the result, where just the observed vegetation is aggregated. And with that small query, you can do such large-scale queries in the data cube without the need to know any programming language or similar things. It's not so easy to learn that query language as well, I know, but it's beyond programming. Okay, other applications would be what we did now already here, looking for events like landslides, storm events, storm damages. You can get different outputs, you can create maps, aggregated maps, you can get curves out of that, you can do semantic content-based image retrieval. Soil sealing is one other thing, and we use that also for agriculture monitoring, harvesting events, mowing events, and so on and so forth. And what we also do here, that we transfer that to other data sets. So in that case, it's Sentinel-3 and AVHR data, where we scaled that data cube to the whole Alpine area. So we have here now time series starting from the 80s, so have more than 40 years or almost 40 years of coarser data, but it works as well. You know, you can also share queries between different data cubes and data. So instead of relying on ARD data, we have the semantic enrichment as our approach to also make transferable queries between different data sources. Here, for example, AVHR and Sentinel-3 used in one time series. Okay. There are some interesting other clients and interfaces we are working on. So mobile apps to do queries on the fly in the field, to integrate that in GIS software, again, to reach users who are not used to complex programming. They are also not used to use Google Earth Engine and so on. So we providing toolboxes to run models in the GIS, and we also teaming up with some other partners for example here, Nature's Calendar. That's a citizen science app where people can, for example, query snow cover measurements. Okay, now coming to the Spotlight C-scale thing we are working on. At the moment, we have that interface and we have some fact bases or cubes attached to that. But also what Guido mentioned before, it would be great to make that more dynamic. So that we can create such data cubes on demand. For example, we have now an earthquake in Syria, we have another crisis that we, for a smaller area of interest, we run a few hours, the pre-processing steps, and come up with such data cubes on the fly, which we maybe don't need anymore later on. For that, we have some development successfully done already. So we have the graphic user interface here easily attached to the different cubes. Now we have to automate the fact-based generation. That is at the moment still a bit an issue. We are working on that. We need monitoring tools for that. We need also workflow tools like Prefect for that to get any errors in building these fact bases. But we're on a good way. Because of the time, I will stop here, but the slides I will provide, we have 4 more slides where the developments in C-scale are depicted or shown, and where we are at the moment and what are the limits at the moment. Okay, I think that's all. Sorry, these are the different fact bases we want to address. And we want to make that much more independent from the area of interest. Okay, so you can look that up. I will share the slides on the web. These https send2cube.at, you get an overview what that is. And if someone is interested also in just try that out and use that, please write us an email. We provide user accounts Thank you.
Thank you very much. Very interesting. Are there any questions for Dirk? Okay. Yes, we'll share the slides afterwards. Yes, please send it to me, and I'll put them in a shared drive for everybody. Thank you. Okay. So let me look at the list. Next is Kappamask. Andres, would you be able to present?
Yes. Share screen. So, can you see the presentation?
I see the presenter's mode. Now it's working fine. Yes, perfect. Thank you.
It's working fine. Okay, thank you. So, basically, the Kappamask is a project of computing, finer scale cloud mask for Sentinel-2 data. And with the C-Scale project, we tried to provide a larger branch of readily computed tiles for the public use. And we tried to cover the whole Europe, at least for some reasonable period. So we have two persons included in this C-Scale project, but of course, during the model development, there have been more major contributions. This is just a part of getting things done in C-Scale. So the use case itself, there is a need for very good cloud masks. That's we have seen this quite obvious. So the Kappamask is basically a machine learning based cloud mask solution, and besides clouds, it can detect cloud shadows and etc. By our test, it has outperformed other cloud masking solutions, but there are still intercomparison projects going on. So but in general, that's our belief. And so yes, we hope that by creating these masks and making them available for the public will be good to have. Okay, how the masking solution works in a very high level. You in the start you have this Sentinel-2. It works both on level 1C and level 2A data. So we need to resample it to 10-meter resolution. Then we split it into tiles and run the prediction model on the tiles, and then mosaic it back together, and we get the 10-meter resolution diff file, which is corresponding to the original source file. Quite straightforward. And here is one example of the output. So the labeling is the manually created cloud mask based on this input image, but of course this particular label has not been used in the Kappamask training. It's just for testing purposes. And yes, at least for this particular case, you can see the difference, how different cloud mask solutions give you information about this particular case, which has both semi-transparent clouds and the cloud shadows present here. Okay, and what are we doing in the C-Scale context? So the Kappamask producing is working fine in CreaDIAS. There is a small Redis queue that shares tasks between workers, so we can optimize the use of GPU and not wait until some data is fetching from S3 or being uploaded to the final location, so that GPU can concentrate on the GPU. There is one instance for CPU, which is doing the data preparation, which is basically the interpolation to the 10-meter grid. By now, we have around 8,000 tiles or these products full products produced. Yes, is still the solution is maybe not fully optimized. I'm not sure we can use the even with a mid-sized CPU that or GPU that we can use the full power. So our current capacity is about 25 products per hour, and we were not able to scale it or get any faster on the larger GPU. But we still hope to put some effort into it. Yes, and of course, as the pre-processing software has not been tested at the very large scales, we still have some failing cases which we need to look into it. But that's a technical question. In general, it seems to work fine. And to wrap up, so what do we expect to get out of it? Well, that at least 2022 we tried to compute for the whole Europe. So what are the benefits from this project? Well, first of all, we want to promote the Kappamask product and get more users for it. So more users mean more opportunities to improve the product and make it more widely available. Then maybe if we have more users, we can think about extending it to some sort of community-driven data set where users who compute the masks for themselves can contribute or whatever. I don't know. We haven't really gone anywhere with that one. It probably makes a good idea to provide this solution in some major cloud providers if possible. Discussions are going on. And yeah, so that's mostly it. If you're interested, I'm happy to answer questions, and you're welcome to try out the software yourself if you're interested. It's open source. The trained model weights are all open source. You can run it yourself, or you can soon hopefully get some examples from the public sources. Or yes, so that's it. Thank you.
Thank you, Andres. I think there was also discussion with SESNet to host the final 12 masks as well, right?
Yes.
Maybe.
Yes. So at least everything computed for during this project will be made publicly available and easily available. Yes, that's the idea.
Right. Thank you very much. Are there any questions for Andres in the audience?
Not really a question, rather I wanted to say, not only to Andres, but to everyone who is here, Cscale is, apart from the rest, also a channel to promote your work and to spread the word to the others. So if you are interested, we can also make a success story out of it, share it through our newsletter, put it on our website, so that more people get to see what you're actually doing. And if you have,
absolutely.
Yeah, because we have a template for success stories and we want to publish them as well. Sometimes we think maybe it's going to be a further burden on you to create this, but actually it's a very good opportunity to promote your work to anyone that anyway comes to the Cscale website, sees our newsletter, whatsoever. So, okay, that was the only thing. And the other thing is, you said that you want to make it available to communities. Do you know how? More or less?
Well, one thing could be that if you say, technically, I could understand how it would work technically, but on the business side or who would maintain it, we don't have a good idea. But we are looking for ways to maybe. But technically, I mean, it would be something that if you want to have a cloud mask, you can your program will be able to tell you if the cloud mask exists, if you need to compute it yourself, and if you compute it yourself, are you willing to provide it back to the community so that not everybody has to repeat the process or something like this, maybe.
So it would be an open data set.
Yes, that's the idea.
Okay. Thank you.
Thank you.
Okay, great. So if there are no more questions, we can then. I have next on my list LOST-Salvage. Yeah.
Sorry, I see a hand from Guido here.
Oh yes, Guido. Yeah.
Yeah, just a question about your difficulties with the GPU processing, because in your case, I find 25 frames per hour a bit low. I mean, I would expect, since you have much less data to transfer, that could be much quicker. So I guess it depends on the number of bands you use, but are you using a specific, I mean, are you programming it yourself, or are you using some existing libraries? Because I think it's very interesting to look deeper into this, right? Because I mean, our project has the same scope, right? It has the idea to do this quickly, and you know, eventually, of course, you could even offer a service that generates the masks on the fly. So you know, I mean, it may actually be interesting to discuss this with some GPU experts. I'm not. I think you are.
Yeah, well, we are using.
Yeah.
Basically, it's a TensorFlow with DeepLab v3 something. I didn't write the software, but it's.
Yeah.
I'm pretty sure there are ways to optimize it.
Yes.
Probably to get it two or three times faster at least. But it definitely needs some effort to put into it. And yes, it is a kind of problem that even if you have reasonably fast GPU, then you cannot really provide the mask on the fly. You still have to wait a few minutes, and that's a problem.
But in principle, that could be brought back to within a minute, I think.
A minute is probably realistic, yes.
Yeah, okay, well, that's worth.
And another thing which we need to optimize is this interpolation to 10-meter grid, which is also, we do it separately now, but this is running on CPUs, and there are probably ways to do it also with the Alus toolbox, I think, but it's also a way that is annoyingly slow at the moment.
Okay.
Yep. In my experience, what's usually mostly the issue with GPU performance is the paging and the how big is the VRAM on the GPU you're using, and how can you stream it. And of course, I/O hiding, talked about that already, but it's very much device dependent sometimes to get really the most out of it. Unfortunately, so a general solution, at least in my experience, always depends on how far you get. But I guess the low-hanging fruits you can probably already collect by grid as suggested. Or just, you know, see maybe there's some streaming you can do.
Yeah.
I don't know how much the TensorFlow supports this, but I know there's CUDA instructions where you can tell it to stream from RAM to over the PCI Express onto the device on the fly, and then you need to chunk it beforehand. Also why I need a profiler to figure these things out.
Yeah.
Okay, good. So I think we can then move on to Bjorn for LOST-Salvage, the next use case.
Okay, can you, I hope you can see my screen.
We can, yes.
Great, so good afternoon, everybody. So I'm going to give you an overview of our project, which is the LOST-Salvage project. Essentially, it stands for Lagrangian Ocean Search Targets in support of salvage operations at sea. This is a project that we started many years ago, developing search and rescue support for the South African National Search Rescue Institute. And it kind of was initiated when some years ago there was a capsized catamaran spotted off the coast of South Africa, and then in response to that they needed some support in terms of finding it, and we developed a particle tracker together with the National Sea Rescue Institute. We built on a particle tracker to facilitate these kind of trajectories and search area estimates. So in the context of Seascale, our objective is to really enable our stakeholders to run simulations or these particle tracking simulations anywhere in the global ocean. So to do that, we're working towards setting up a simple interactive dashboard, combining, for example, Jupyter notebooks with something like Voila, or alternatively going for these data APIs like Streamlit and Greppo to enable user interactivity. And then part of the C-scale activity will be to make the global wind and ocean forecast, hindcast and forecast data available on a daily basis, so you can run these simulations anywhere in the global ocean. And then once we've set up this dashboard, the idea is with our partner, which is LOST-Salvage, which is a salvage company based out of South Africa, to pilot an operational support service for salvage operations. And sort of in parallel, what we're doing is we're working with the naval engineers from LOST-Salvage to improve the accuracy of the LOST simulations. So a little bit of background in terms of what we've got and what we've done is what we call LOST is essentially a particle tracker built on top of something called Ocean Parcels, which is a particle tracker developed at the Utrecht University. And then we work together with the National Sea Rescue Institute in South Africa to add essentially the leeway, which is how different objects in the ocean respond to the wind forcing. And then in a sort of proof of concept paper, we published a number of use cases demonstrating that this combination of leeway with ocean parcels and Copernicus data actually gives you relatively good estimates of where you could expect to find objects that are lost at sea. And here in the example, this on the left, you see an example of our typical workflow, very simply put. And on the right, you see the examples of the simulations that we've run. The gray lines here are the sort of the ensemble, the different. So we deploy like hundreds of virtual particles at the location where the the capsized catamaran was spotted, and then we simulate those hundreds of the different trajectories, and then if you calculate the mean, we actually were able to get very close to where the capsized catamaran was eventually found again and salvaged by the National Sea Rescue Institute. And then these are the kind of statistics or decision support tools or analytics that you could provide. Here you give a percentage of the density of particles in a given area. So for those of you that are interested, you could read the full paper over here. Then the next step, what we did is, because this is a bit of a labor of love, we proposed a hackathon challenge in Cape Town, where there was this Ocean Hub Africa set up a hackathon, and they asked for a challenge, and we put together a challenge to build essentially a front end for this for the LOST capability. And our hacker team came second, and in 48 hours they essentially put together a draft front end for us to work with. So that's essentially what we have at the moment. We've got a whole bunch. We will use a whole bunch of data. We've got the model simulations, and then the hackathon built this sort of prototype starting point for an API and an interface for users to more easily run these simulations. So this is what we've got. We've got a whole bunch of building blocks that we're now gluing together in the LOST infrastructure towards creating kind of like LOST as a service, where people can go and in a very simple dashboard select which kind of object they're looking for, plug in some longitude and latitudes, and then some times, and then the system should go and run the simulation and return some of these analytics. So here, in fact, what we're doing in terms of getting the forecast data and the hindcast data, we're actually reusing some of the functionality and scripts already developed in C-Scale as part of the high sea use case that Lorenz presented earlier. And then this is a command line interface that we use to run the particle tracker. So in terms of status, we've got a whole bunch of tools and scattered scripts that are lying around that we're gluing together into a workflow. We already have access to the INFN OpenStack, and our next steps are essentially to set up some virtual machines and Jupyter Hub interface so that we can start developing the dashboard. Then we will set up a workflow to download the global data on a daily basis and archive those on the C-Scale infrastructure for further use. And then we will go forward and build the interactive notebook for non-technical users to run the simulations. And then sort of as a final product, this is kind of what we're after, a very simple interactive dashboard for users to run a LOST simulation anywhere on Earth. And then this little video is kind of a demo of what can be done with these kind of tools. So that's where you're going. Very short and sweet, I'm afraid. There was not that much more to show. Thanks.
Thank you, Bjorn. Very nice. Are there any questions for Bjorn?
Irrelevant, but very quick. I'm very curious. What happened to this catamaran? Why did it turn around?
It's actually quite a sad story. The catamaran sailed from Cape Town to Indonesia and or Australia, I believe, and somewhere off in the Indian Ocean it got caught in a storm and got capsized, and unfortunately everybody on board was lost. And then it was spotted a few years later off the coast of South Africa, and then we were trying to find out how to salvage the catamaran. And the NSRI, in fact, was able to find the catamaran, and then when they tried to tow it back to port, the cable snapped, and then they lost it again.
Oh yeah.
It's
Okay.
a real, it's a bit of a horror story. Yeah.
Sebastian.
Yeah, go back to the use cases, and then we have GLTFCA, biocarbon. So I guess I think we have here with us Marius. Maybe Marius, can you present, or is it going to be Lucy?
Hi everyone. Marius, are you there? Marius was going to speak. He's been more involved with the C-scale so far. Not sure if he's not available. I'm afraid we haven't really got much to report as we haven't really started yet.
Yeah, that's not a problem. It's giving a brief overview would be very nice anyway.
Yeah.
But if Marius is not available, we can then jump to Nivar.IA, and that's going to be.
Yeah, that would be great. Maybe he'll be back on in a second. Sorry, I think he has load shedding.
Exactly. So we can go back to Marius after this presentation. Thank you. Okay, Miguel. Hello.
Hey everyone. Okay, let me share my screen. All right. Can you see that? Yeah.
I see it in the presenters mode.
Yeah, let me. Okay.
There you go. Yeah, all perfect. Good.
All right, thanks. So I will be presenting today Nivar.IA's use case, but together with me, there's also Alberto. He will be also checking the chat if there are any questions during the presentation. And of course, we will try to answer them all afterwards as well. In any case, we're also in a very early stage, so that's as a disclaimer. But thanks very much, Sebastian and all the team, for the opportunity of being here and all the help that you are providing to us. So for our use case, in fact, we're both coming from a technical thematic background, from the agronomic and environmental engineering perspective. But we both shifted to a software engineering approach, and this is what we're doing in our day-to-day. We noticed that there are a lot of situations where there are very, very highly qualified people trying to work on spatial data, but they're finding some challenges when maybe trying to scale up on both the spatial and temporal point of view, and also when dealing with all the tools that are within that process itself. So our target is to build an open data platform and tool that can scale up, mostly for agronomic and environmental algorithms, dealing with big data through a no-code or low-code tool. This is mainly so that scientists can focus on science and not really on software or infra. So the product vision that we have is basically composed of three main steps. So the main step would be to add layers, aggregate them, and so on. We will talk about this in a bit. And also to then analyze, combine data sources and build models. And finally, scale and deploy these models, right? So on the first step, what we're willing to deal with is some layers that will be pre-generated and made available by us, like vegetation indexes, digital elevation models, some socio-demographic data, maybe POIs and so on, self-curated algorithm and data products like maybe burned area detection and some others. And we're also planning to offer the users the possibility to do a live fetch using OpenEO. We're doing all this through a very specific standardized format, which is not really meant to be used by design for raster data, but we are pre-processing it to get this format. And let me very briefly show you how that looks like. I have here an example. This is NDVI data for a Sentinel-2 data source in a specific area in Spain. This is 10 meter resolution. And here we can see how by using this format, we can not only visualize, work in an interactive way with the data, but also we can do things like aggregate and deaggregate. This is being done on the fly, so it's pretty performant. We can, of course, then filter the data out and all these kind of capabilities. But the most important side of things when dealing with H3 data is that because we're dealing with a standardized format, we can access properties like neighbors and so on, parent and children of each grid cell, which brings a lot of flexibility when working with models that are going to be implemented and performant and at scale. So the second part of the analysis would be to allow users to define an area of interest, combine data sources, because all of them will be sharing the same grid. So this will be basically a join behind the scenes, do some calculations and analysis, train and test ML models, and evaluate and export the results. And then once they know what they want to actually analyze in a certain area, users will be able to extrapolate the analysis to a bigger area of interest, run, if they want, the train and test phases on a bigger area, and predict with ML models or their analysis, and then finally run on a schedule and publish the results. So on the technology stack side of things, what we're using and planning to use right now is Prefect as the orchestration layer. For pre-processing, we're having OpenEO also not only for pre-processing, but also as the data provisioning tool. We're going to use Dask deployed to Kubernetes for some pre-processing that needs to be done on our end. As the main layer, and everything else will be happening in-house. We're using PostgreSQL in a Kubernetes deployed manner. So we're basically going to be based on the cloud native PG project. And then for in-house processing, we're going to use dbt together with PostgreSML. And then, of course, we have all the side of things of the application with a backend in architecture on multiple microservices for the backend APIs using Fast API, and then going to use Carto and React for the front end and data visualization side of things. Most of these components are open source based and are offered and worked through OpenStack. So yeah, I know that it was quick, but if you have any questions.
Thank you, Miguel. Any questions for Miguel?
Hi.
Yeah.
Hi, I'm Alberto, fellow of Miguel. Through the different presentations, we saw that most of the process or the modeling or analysis part were done using Dask, Python on Xarray. We in this project we are using another approach, that is working in-house the database and trying not to move around the data, but rather work where it is. So I was wondering if there is another experience. I mean, for example, I saw for unfollow Jux, I think from Pangeo project, that they were using some similar tools. So I was wondering if they had some tests or some experience in using in-house or using a database rather than moving the files to another clusters and work on them.
Okay, that's a question for Anne. Anne, are you around?
Yes, I mean, I'm not sure I can fully answer to this question, madam. Yes, the main goal here is to work open science. So what we want is to anyone can access the data from anywhere, and this is also why we have this approach. Like the DAS deployment can be customized for users depending on the compute needs. But it doesn't. I mean, for me, this is not orthogonal approach. This is more a complementary approach, because you can still have the data in a database, and we have data somewhere. So I'm not sure I fully understand your question.
So I saw that most of the project I focus on Pangeo because you saw a technological stack, like a lot of different tools. So I realized that most of the project focus on moving the data to some cluster and then apply some processing on this cluster. So do you need to take the data, move it, processing, and put it back to some general storage or something like that? We have seen some buckets, databases, or just simply the file on file disk. So we are using another approach. So I was wondering if someone here, I thought of you because I enjoy your presentation in Pangeo. So I was wondering in this comparison of approaches, working in-house, let's say, all inside one database, compared to working with files and moving around in some cluster. If someone has tried this approach, that working in-house, and if they have some experience, how was the performance? Or I don't know.
I mean, I don't know how much it scales. I don't know how much it scales when you have large amount of data with a database, but I think it's not a bad approach. If you have the data close to the compute, it's always more efficient. The point of like Pangeo is to be more accessible to everyone and to understand how we can make fair and open science. And in this context, when you have everything localized, this is more complicated. And I don't say this is not possible, but it's more complicated.
Oh.
And I would be also interested to see how you see this aspect for your project.
Yep, I think just to add on top of this, I think both Alberto and I come from an enterprise world, and we're seeing how large clients with large data flows are starting to move from an ETL perspective to an ELT one, just because right now database and modern data warehouse have shifted. Right now the capabilities are different, and we're curious to see if this is also being in a horizontal way transferred to other stacks and tools in the context of OpenEO and Zscaler. But it makes sense. What you mentioned makes total sense.
Thank you.
Thanks.
Thank you both. Okay, so final check if Marius is around to present DLTFCA. I don't think so, but I don't think.
Hi, can you see?
Oh yes, okay, good.
Yes.
Sorry
guys. I've been experiencing some technical difficulties, but I'm back.
Okay.
And I have to apologize. I didn't really prepare a presentation. We really only started this project now. But let me give you a bit of a background. The GLFTCA stands for the Greater Limpopo Transfrontier Conservation Area. So it's a large area. It's about a study area of 10 million hectares in Mozambique. I wish just before my computer crashed, I had a picture for you on where it is. Unfortunately, not now anymore. But basically, we're a red development company, mostly centered in Africa. And we've just completed the feasibility study for this area for a red project. We're just busy with the last deliverables at the moment. So our main aim, I think, with this project is to really look at deforestation, but mostly actually degradation, forest degradation in Mozambique. And the reason why we wanted to look at it is because it is fairly difficult to detect, not just because the area is dry forest, as it is known mostly, but it is also, it's not as tropical forest, so easy to identify deforestation from remote sensing imagery. And also because degradation is much more subtle than deforestation. And I'm sure those of you who work with it know exactly what I'm talking about. And basically, I think our approach first to start off with would be using this avocado algorithm. It's an anomaly vegetation change index, or the change detection algorithm that's been published, I think, last year before, by De Kuiper et al. So that would be our entry point in trying to quantify. I think our main aim with this is to quantify, first detect and then quantify degradation. I don't know, in Mozambique, a large portion of the degradation happens through charcoal harvesting and timber extraction, lots of illegal activities going on. And if we can have a handle on detecting and especially quantifying that, that's our main aim with this project. Basically, in terms of technology, techno stack would probably be, we're just working in R, and we just managed to set up a VM this morning with Sebastian. So looking to start pretty soon, and also looking to collaborate. We've had some very interesting other presentations today. So especially, what was it from, I don't know if he's still here.
I don't see me looking around, yeah, but the return use case, yes.
Yes, we'd really love to engage and see, because we're really open to more. This would be just our entry, entry point, and see what we can do. I see the algorithm already uses Landsat. I think we've interpolated that with some Sentinel images, but I think we're really only starting off, and looking forward to update you on how it progresses.
Okay, very good. Thank you very much, Marius.
Thank you.
Okay, so I think is there any question for Marius? Okay, I don't think so. I'm really sorry, it's a bit later than expected. But anyway, it's been very interesting so far. So I think I'll email you later with asking for permission to share the video if you don't mind. Also the slides, so we can share them. And just to remind everybody what Kara mentioned before, if you have any success story that you'd like to promote with CSK, we're happy to use our channels to promote that. So anything else that you'd like to say, Caris, before we close? No?
No, thank you very much. First of all, for the idea, for coming up with the idea, and for all the presentations. I had to jump out for some time, but what I listened to was very interesting, and I hope it was useful for the users to exchange a bit between each other. Yeah, if you want to use Cscale as a channel, we have some templates, so it could make your life a bit easier to promote your stuff. So come in contact with us. Thank you very much to those who provided the data management plans. I know it's a little bit tedious, but thank you. And that's it. Have a nice day, basically.
Yeah, thank you very much, everybody, for preparing the presentation and staying that long.
Yes.
It's been very nice. Well, have a nice day, and talk to you very, very soon. Bye-bye.
Thank you. It was very interesting, actually.
Thank you.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye.
Bye-bye.